Okay, so the plan for this lecture is to do essentially just 4 examples of applying Gauss's law. This really is just, this is going to be a lecture in lessons in symmetry and how we can use relatively simple concepts to make some quite profound statements about what charges are doing inside conductors, for example. So let's review the concepts first before we go on. So this is all related to this idea of electric flux, which you can think of as really just counting field lines that are piercing the surface. And we talked about how this necessarily must involve some sort of dot product, whereas you have some sort of surface. Should have had a surface ready to go. Here's the book again. Right, you have some sort of surface, and I have an electric field that's piercing it at some angle. Part of this electric field is perpendicular to the surface. That is really piercing. But part of this electric field is tangent. That's the word, tangent to the surface. And so as a result, that part of the electric field does not pierce the surface. You're only looking at the part that's perpendicular to the surface. The dot product is designed more or less to be able to extract these sorts of things. And we were able to do that by defining this normal vector, which you'll either see as kind of little dA when we're dealing with calculus. You might see it as kind of a capital delta A when you're dealing with kind of a macroscopic slab, like a rectangle. Or you might sometimes see it written as with a little lowercase n, which it usually corresponds to the unit vector direction of this little patch. And again, let me just draw one up here. If I have some rectangular slab, I can specify one vector that tells me something about that slab by defining a vector that is perpendicular to the surface. So this vector makes a 90-degree angle with the surface. And this vector, sometimes you'll see it written as kind of like n hat. So that is a unit vector that is perpendicular to the surface. And then, so n just is telling you the direction. And then this connects to what I was calling delta A or dA, in that the magnitude of this vector delta A is equal to the area of the patch and then that points in the direction n hat. So again, that's just kind of taking and writing a vector as a magnitude and a direction. This area vector, dA, delta A, what have you, has a magnitude that is equal to the area of that patch, which might be a big patch, or it might be a calculusal infinitesimal patch, which then the area is just a little dA. And it points perpendicular to the surface, and n, lowercase n, is kind of a common reserved letter that we use for vectors that are normal to the surface. Remember, normal is just a fancy word for perpendicular. So if we can then calculate this flux, and if we have a surface that has multiple sides, it could be a finite number of sides, like take a cube. There are 6 sides. Each of those sides has a normal vector, a vector that points perpendicular to that part, that one side. And the convention is that when you have a surface that encloses a finite volume, like a cube or a sphere or a cylinder, right? There's a finite volume inside the object, inside that surface. The convention is that the normal vectors always point away from the volume. So for this kind of prism thing over here, if I were to define the normal vectors, in this case I would say there are 4 sides to this thing. There's kind of this kind of diagonal side, which kind of might have a normal vector, looks like that. So that might be kind of delta A1. It's perpendicular to that kind of diagonal side. There's this vector, this side, call that delta A2. There's the one in the back, delta A3, and then there's the one that is on the back side. I might call that delta A4. each of those vectors, if I take the magnitude of each of those vectors, it will give me the, it will be set to equal to the area of each of those patches individually. Oh, wait, I forgot one. So what about the base? And there's also the base as well. So there's 5 sides, sorry. In this case, the magnitude of each of those vectors is equal to the area of each of those sides, and then each of those vectors, notice, are pointing in a different direction, which you could specify as a vector. If you have a smoother surface, or you're dealing with electric fields that vary, in space, then again, you can take any area, which doesn't have to be, like, it could be something that's curved like this, and I could break down the side of this cup into a bunch of tiny little rectangles that are, each of them, if I zoom in enough, I look at them, and each of those little patches are more or less just a flat little rectangle, or a flat little square. And then that's where calculus comes in. Integral is a fancy word for add up all the things. I'm adding up all these fluxes, which I might have to do, right, if it's, whether it's a closed surface or not. I can take, this kind of cup, for example. It's not a closed surface, I can, because there's a hole here. But I could still talk about the flux, say, through, the side of this container, again, by taking it and kind of breaking it into a bunch of tiny little areas and adding up the contributions from each individual patch. When it is a closed surface, and again, this kind of like this circle here is a statement that this is an integral over a closed surface. How do I know it's an integral over surface? Because that's what the dA is, right? Remember that whatever's after the d tells you what you're integrating over. In this case, we're integrating over area. So we're looking at patches of area, an integral over dx. We're looking over values of x, across the number line. An integral of density over volume, a dV, right? We're looking at a bunch of tiny little cubes and we're adding them all up. So if we evaluate this integral of the flux over all the patches that make up this surface, this closed surface, Gauss's law says that that connects to the amount of charge that is enclosed within that surface. It doesn't say anything necessarily about how the charge is distributed within the surface. It just tells you that if you were to look inside that surface, inside that finite volume it's enclosing, you would find some net charge. And you're able to do that just by looking at the flux of what's going on kind of at the surface. Right, again, to take kind of not electromagnetism example, right? I'm sitting in this room. This room, I can imagine the walls and the ceiling and the roof are forming a closed surface that's encapsulating me. If everything was turned off, and I wasn't in here, eventually this room would, reach the same temperature as, say, its surroundings. But since I'm in here, and I'm moving around, I'm giving off energy and I'm heating up the room, and that heat eventually kind of makes its way through the walls and through the ceiling and the floor and the windows, mostly through the windows probably. So by looking at what's going on at the edges, right, if we notice that there seems to be a lot of heat coming out of these windows, that suggests that there must be something inside that is creating that. That might be kind of a thermo example of this idea. By looking at what's going on at the edges, we can say something about what's going on inside. Again, kind of abstract, very powerful. And notice that Gauss's law, and this will be kind of like a goal for today, I've never stated kind of what this surface has to be, right? I just say that's a flux over a closed surface. I don't say it has to be a sphere or it has to be a cylinder. The flux over any closed surface connects to the amount of charge that's within that surface. If I draw a sphere, I'm saying something about how much charge is inside that sphere, as long as I calculate the flux coming in and out of that sphere. If I use a different shape, same thing. If I use this cube, I'm saying something about the flux. If I look at the flux going through each of these 6 sides, I can say something about how much charge is inside. If I change the shape, I'm measuring something different. But it doesn't matter what shape you use. Furthermore, it doesn't matter whether or not that surface is an actual physical surface. In this case of this cube, the idea of the surface is very clear, right? There's an actual edge to this thing. But I could just imagine this point in space, this space where I just kind of hold this cube in your mind's eye and imagine it's still there. Right? I can draw that same outline of a cube and it'd be a closed surface, even though it's kind of, the ghostly remnant of what used to be there. But I could still use that as a surface. I could calculate the flux kind of going through these invisible 6 sides, and that would then allow me to say something about the amount of charge in this part of space. So that's where the abstraction comes in. This surface can be anything you want, as long as it's closed. And it doesn't have to actually correspond to anything physical. It doesn't have to be an actual surface, like this table. I could just draw a box, an invisible box in the air with my hand, and imagine calculating the flux of the electric field through that invisible surface. And then that tells me how much charge is in that region of space. So I think I actually might as well just write that down. So for Gauss's law, any surface will do, as long as it's closed. And it doesn't even have to be a real surface. I say physical surface. The idea being, again, that you can draw kind of any surface, and as long as it's a closed surface, the flux through that surface then connects to the amount of charge within it. So we're going to want to do this, right? This is written in the language of calculus, but again, this tells a story. You add up all the fluxes, right? This is the definition of flux through a tiny little patch, a patch of very small area where we've made the patch small enough that the electric field is uniform over that small patch. You might be doing something more, might be changing on a larger scale, but I can always zoom in enough so that it's a constant, and then look at a bunch of tiny little patches where it's constant over each of those patches. As long as I take all those fluxes through all those little patches and add them up, and the surface is, encloses some finite volume, I can say something about the charge inside. We've dealt with electric fields. We now, I think, have some comfort with these normal vectors and kind of how you define them. Remember this dot product? Let's go to this example here. This dot product, the definition is that this is the same thing as the magnitude of the electric field times the magnitude of this area vector multiplied by the cosine of the angle between those two vectors. That's in the definition of the dot product. So when you have a patch like this, I can define a normal vector that points perpendicular from that surface. And then if there's some electric field, some uniform electric field that's also going through and it's piercing that rectangle at some angle. But it's ambiguous to what that angle should be if I'm just looking at the electric field vector in the surface. What angle do I use? It is not ambiguous if I think of it in terms of what is the angle between the electric field vector and the normal vector. So this one vector and then this electric field, I can always move vectors around, so I can pick them up and put them kind of tail to tail. So there's the area vector, there's the electric field vector. And again, this is kind of a 2D picture, but you can imagine that, right? It might be, this is kind of 2D, but then it might be kind of have some 3D component too, right? Where it kind of does something like that. But nonetheless, there is a single non-ambiguous angle that exists between those two vectors. And that's what the dot product needs. So if a problem tells you the angle, some angle that the electric field is making with the surface, you have to be careful. You need to make sure that you are calculating the angle between the area vector in the electric field. So then, if you have, for a given patch, you've defined this area vector, which in this case, right, that's some macroscopic area, so I might use capital delta A instead of dA. And then if the electric field is a constant through the surface, then the flux through that patch, right, through this one single patch, is then, right, integral just means add up all the things. So then there's only one thing to add up, the flux through that single patch. So I have the dot product of the electric field with this normal vector. The definition of the dot product says this is just the magnitude of E times the magnitude of that vector times the cosine between them. We've now kind of defined kind of how that angle is not ambiguous and defined. And then that is the flux through that particular surface. And then that just might be one part of a larger problem. So the idea is to do some examples because while this integral of Gauss's law can be very challenging, when you take Calc 3, you'll have these kind of vector calculus identities that actually a lot of them were motivated by the study of electrodynamics, such that one of them I think is called Gauss's law, and it relates to similar integrals that look like this. So Stokes' theorem and Green's theorem, other things that you'll do in upper level E&M. So what we want to do in this course, which I think actually is the best of all possible cases, because I'm not focusing on the math for the sake of doing math. I'm focusing on the concept of I need to evaluate a flux and translate that into saying something about charge, or vice versa. If I can say something about the charge enclosed, I can say something about the flux. Let me go, and then there, so we're thinking very geometrically. So there is how naturally symmetry, if we have it, can be very powerful. Let me just do a somewhat abstract example. It's not that abstract actually. Suppose I have a, so let's have a kind of single charge Q. So I have some charge Q. Let's just say it's positive. Why not? And I could ask myself, what is the flux through a sphere around that charge that's a distance r away? Again, here I'm just kind of focusing, this example is starting just kind of thinking about flux. So you can imagine if I were to draw a sphere around this charge, and again, it doesn't have to be an actual, I don't have to go build a sphere, but I could just imagine, right? Imagine the ghostly outline of a mostly transparent sphere that kind of is surrounding this charge, and that is going to be my what's called sometimes called a Gaussian surface. All that means is that we're imagining some sort of closed surface to then use in Gauss's law. Because again, I can use any surface for Gauss's law, so I'm going to state the one I'm going to use. So something called a Gaussian surface. Not that it's anything special about the surface, just that's the one you're choosing for this problem, and it doesn't necessarily have to exist, right? There's some ghostly, ethereal surface I'm imagining around this charge. In this charge, I know what the electric field for this charge looks like. I know that there's an electric field that is kind of radiating away, or rather it's kind of in the radial, moving the radial direction away from this charge. And some of those arrows eventually kind of pierce through the surface. I can then imagine there is a flux. There's a net flux through the surface. There are more arrows coming out of the surface than there are going in. There must be a positive flux by our definition. So, by Gauss's law, I know that the flux through the surface. Right, so this again is the flux through the sphere must be equal to the charge enclosed, which is Q, over epsilon naught. Which in this case we kind of decided was positive because we said this was a positive charge. So then, without saying anything else, you can already determine that the flux through this red ethereal sphere is some value. What is it? Q over epsilon naught. And then if you actually went and figured out what the electric field is at each part of the sphere, you could calculate the dot products for all those patches. Imagine taking the sphere and breaking it up into a bunch of tiny little rectangles. There's billions and billions of these little rectangles. Add up all those fluxes. You get some number that is equal to Q over epsilon naught. So again, here I'm just using definitions. So flux through sphere, and I'm going to make sphere red, just to remind myself that this is the flux through this particular sphere. Now imagine I draw a bigger sphere. How busy is this going to be? Oh well, here we go. Suppose I draw a bigger sphere around the same charge. And I could ask, what's the flux through that sphere? Well, I know the electric field is kind of going out from the positive charge, and it's getting spread out more because the electric field is getting weaker as you go out. But now I have this bigger area that I have to ask, how many field lines are piercing this larger area? Well, I could then do kind of the integral of E dot dA. And this then is the flux through the blue sphere. It's a bigger sphere, the electric field has a different magnitude, but it better be equal to the amount of charge inside that sphere, Q, or epsilon naught. This flux evaluation better be exactly the same. At least when you do, when you do that integral. And then here's where it gets even more cool. Let me move these over. More cool. Yeah. So suppose I have, we're going to draw spheres. Let's see. Let's move this and everything down a little bit. I lost my Y. So now let's imagine, I could imagine another sphere, but I'm going to make that sphere, I'm not going to put the charge in the center of the sphere, I'm going to have it be offset. So I might have kind of a sphere that, yeah, this is way too busy. I'm just going to redraw it. So here's a copy of the charge, same charge Q. The drawing's getting too messy. And then imagine I draw a sphere, but I have the sphere kind of offset, but the charge is still inside. So we have an offset sphere. With kind of Q still inside. Well, I could ask myself, what is the electric field doing in terms of how it pierces through the surface? And it's still going to be piercing through, but as it pierces through, it's not quite as, it's not the uniform case that it was in the previous two examples. Where you can imagine in the previous example where everything was kind of concentric. The electric field is the same everywhere along each of those spheres. That will be key in a second, actually, for the next example. So you can imagine all those dot products are actually going to be the same thing. Where in this case, the electric field vectors that you're drawing, as they eventually pierce through the sphere. Let me try to draw, maybe I'll draw like little red patches. So this one on the left might go through this little patch here. This line eventually pierces the surface there. Maybe this electric field line kind of patches that surface. This one might eventually pierce through that patch, this patch, and maybe this patch, I don't know, on the back side, perhaps. So the electric field is going through the sphere, kind of not, right, you know, they're going, each electric field vector is going through the sphere at a different angle, and it's each, you know, where it pierces the sphere, you know, for each patch is a little different, so the magnitude of the electric field is different through each of those patches. So computationally, this integral, if we were to do it without any other knowledge of Gauss's law, would be a very, very, very hard integral to do mathematically, because you'd have to take into account this offset and, you know, everything I was just talking about. But Gauss's law, I know that this must be equal to the charge enclosed divided by epsilon naught. I know that the flux through this offset sphere must be exactly the same as the other two examples, the blue and the red sphere. Now, through every little rectangular patch, it is not the same, but they all must add up to be the exact same thing. Just as, last example of this, same charge, Q, and I say, screw spheres. I'm gonna draw a cube. And maybe I'll put the charge more or less at the center of the cube. I actually doesn't look like I drew it at the center. So it's kind of it's kind of somewhere near the center. But notice how I'm saying maybe it is, maybe it's not. Doesn't matter. Because again, as I look at, you know, the electric field vectors that eventually kind of pierce through, you know, the cube, and kind of goes through, you know, patches of the cube, you know, but at different angles. Maybe there's one here that kind of pierces through this kind of front-facing side, and this one kind of goes through the side here. All right, so you could again calculate all those electric fields and what their direction and magnitude are when it gets to the rectangle, and then the electric field is changing, so I can't just consider 6 patches because the electric field is not uniform over any one of those patches. I have to then take each of those patches and break it down into a bunch of small little rectangles like I've been drawing. But why do that when I know at the end of the day the flux through the cube has to be equal to Q over epsilon naught. The flux through the cube is exactly the same as through all the other surfaces. That is saying, I think, something, why this thing can be so powerful. Because again, I'm connecting kind of something that can be very complex mathematically, dot products of vectors and integrals over it, to something that is countable, you know, counting charges. And notice that I didn't really have to specify anything about where the charges were inside. As long as they're inside, that's all I really need to say. Then another example, then I'll move on. Right. Now let's take same cube, but there's going to be 2 charges in here. There's one here that is equal to 2Q. That's a positive. And then there's another charge somewhere else in the box that is equal to negative Q. In this case, there are 2 charges plus 2Q and negative Q in box. And again, to try to nail the point I'm trying to make, right, and I'm stating that this happens to be the same box as above. What is the flux through the box? Has it changed? before there was only a single charge and I calculated the flux through that box, I said it was Q over E. Same box, but now I've changed the charges inside the box. But notice the net charge is still just Q. Q net, which is kind of the total enclosed charge, is still just Q. And so, as a result, the flux through this box is equal to, again, just Q over epsilon naught. Even though that is a vastly, dramatically different looking electric field compared to when it was just a single point charge. You know, this is some sort of dipole, which has, red's not good use with purple. Right? Some sort of dipole that's kind of an offset dipole. So you imagine kind of field lines. Oops, I drew those arrows the wrong way. Just these arrows go in. These go out. Right, so you can imagine there are some field lines that are piercing the surface and looping back around and going back in, and a very different looking electric field compared to a single point charge. Yet the total flux is still just Q over E. Wow, amazing. Right, so again, if you know something about the charge enclosed, right, you can say something about the flux through any surface you draw. Right, make the cubes bigger, move the charges around. Right, I could do another example where, you know, I have a single charge and I just, you know, pick a random spot. You know, I roll some dice to determine where inside, you know, the box I put the single charge. The total flux through the box does not change. Again, the flux through, you know, an individual little patch will change, right, if there's a charge nearby versus far away. But again, Gauss's law is saying something about the sum of all the patches that make up the surface. All right, so that was an example I did not intend to do, so I guess we get 5 examples today. So let's do I'm actually going to now prove Coulomb's law. I guess I'm not really Coulomb's law. I guess maybe we'll call it Coulomb's law for E fields, which said that, you know, electric field for a point was equal to Q over 4 pi epsilon naught times the radial distance away. So I might write it like this, where R points away from Q. And again, if Q is greater than 0. The convention, right? Radially outward or radially inward. And of course, there's a mistake because I went too fast. This should actually, of course, be R squared. You know, we got that for a point charge because we kind of had to assume Coulomb's law for two point particles, and we had that force, right? KQQ over R squared. Remember, K is just 1 over 4 pi epsilon naught. And then we define the electric field as the force divided by Q. So then we got Q over 4 pi epsilon naught times R squared. Let's now prove it. Yeah, that was kind of arrived at by experimental verification. Now, if we take Gauss's law, we can prove that. And it relies on our knowledge and the power of symmetry. So let's consider a point particle. Now let's suppose we don't know anything about what electric fields look like. We know it's a point particle, and we know it has some electric field, but we don't know what that electric field should look like. And for the sake of drawing, let's let this be charged. Let's let this charge be a positive charge. Though that doesn't matter, but the arrows I draw might just have different directions if it's negative. This alone, I could just ask, I have a point particle. What should the electric field look like around a point particle? You know, a point particle which has kind of no volume by definition, it's just a point. And a point looks exactly the same no matter how you look at it. You can think of it like a little sphere, right? A sphere, if you have a perfectly smooth sphere that's kind of uniform in color, no matter which side of the sphere you look at, you see exactly the same thing. It looks exactly the same no matter how you move the sphere around. And then just imagine making that smaller, smaller, smaller. A point particle has a three-dimensional symmetry, right? It doesn't matter kind of where and how I look at it. It always looks the same. By this symmetry, that means, right, the idea could be, and maybe I'll stick with using a little sphere so we have some sort of thing to look at. Do I have a uniform sphere somewhere? And this bag of tricks. Yeah. It's not really uniform, but it'll work just fine. So I have this sphere, right? And I want you to focus carefully on whether or not I rotate it or not. So I could have this sphere like this, and we're looking at it, then I tell you to shut your eyes. And after a while, you can open them again. You would not think that anything has changed. This looks exactly the same, again, by the symmetry of it. Now I could ask you to close your eyes again. And when you look at it, I could ask, has anything changed? And because of the symmetry, you would say, nothing has changed. You would not know if actually, when I asked you to close your eyes, what I had done actually was twisted a little bit. And actually I did, right? When I closed the cam, I kind of just twisted it in my hand a little bit. But I bet if you go back and look, unless you focus on like the dust that's on this thing, you would not be able to tell any difference in whether or not I had moved this thing or not. When you shut your eyes and then looked at it again, shut your eyes, looked at it again. In that case, the first time I rotated it a little bit, the second time I didn't. That's symmetry. So, what does that mean for the electric field? That means that we can say the electric field must be kind of radially going outward from this charge. So a point particle must have a radial electric field by symmetry. Because you should be able to close your eyes and then open them later, and whether or not I rotated it, you wouldn't be able to tell the difference. Therefore, whatever the electric field looks like has to have that symmetry as well. Let me give a counterexample, or an example of how this would manifest itself if there wasn't symmetry. Right, suppose I have some charge Q, and maybe the electric field kind of looks, it's all going out from the charge, but maybe on the left side, the electric field is stronger. All right, so maybe it looks like that. Right, more electric field lines on the left compared to the right. Now, if you close your eyes and then open them again, you would see the exact same point charge in the center. So you would say, well, there needs to be more electric field lines on the left and less on the right. Else, what are we doing? But then if the electric field did look like this and I rotated the charge, the electric field should then rotate with it. So this does not have symmetry, or this doesn't have spherical symmetry. So that doesn't seem like that could work. Because if I rotated it secretly, you wouldn't be able to tell I rotated the charge. But then if you did see that the electric, right, I could give it, another version of this is I'm holding a charge and the electric field is stronger on one side than the other. You close your eyes. I don't move anything. So you would expect when you open them to see the exact same thing. But then if the electric field is different when you open your eyes, you would say, okay, you did something. But it doesn't look like you rotate it at all, because again, this is a point particle. This is the idea with symmetry. So let's now use this to our advantage. When you're doing Gauss's law problems with symmetry, so symmetry with Gauss's law. Is, you want to evaluate this integral, which involves this dot product of this electric field over patches of the surface. The surface could have millions and billions of little patches if you have to do kind of a calculus thing, or it might have kind of bulk macroscopic sides. So kind of the power of symmetry with Gauss's law, right? Essentially, you want to try to pick a surface so now you want to try to make your life as easy as possible. What's a way to make this integral really easy to evaluate? If it's equal to 0. So try to pick a closed surface. I should say closed surface. Again, that's how you use Gauss's law. It has to be a closed surface. Try to pick a closed surface so as you look at the different sides of the surface, so that E dot dA equals 0 along some sides of the surface. Again, think of a cube, right? Pick the right cube and orient and rotate it such that maybe the electric field is, the flux is 0 through some of the sides. Which again, when does the dot product 0? That's when the electric field is perpendicular to the area. Which again, if that dA is defining, it doesn't say that's where the patch is, right? If this is dA, then the patch is here. So then if the electric field is perpendicular to this pen, the electric field is tangent to the side. So it's not piercing the side. So you want E to be kind of perpendicular. Ideally, maybe E vector is a constant along other sides. And that's usually where symmetry can be helpful as well. Pick a surface such that the electric field, while it might be changing direction, it has a constant magnitude over the sides, because then the dot product just becomes a constant times dA, and maybe times cosine. Integrating constants is easy versus something more complicated. So why did I feel like I had a third example? I guess thinking of an example we'll do at the end. Or, right, maybe a case where E is just identically 0 along other sides. Because again, then that's like kind of item 1. You're just adding up a bunch of zeros. So then let's go back to this point particle. Here's a point particle. And I now know, I've justified that, I'm leaving myself enough room to write. Let's move this over. That by symmetry, the electric field points kind of radially away from the charge. And again, by the symmetry of, I lost the ball. There it is. Right, and again, by symmetry, we know it should look the same in every direction. So the electric field lines, the number of them in this direction better be the same as the number in this direction. But then also the magnitude can only depend on, at most, r. And the magnitude of E can depend on r only. Right? It can't depend on, say, the direction, right? Because then again, we said it has to look the same no matter which direction you're pointing or looking on, on each side, on the sides of the charge. So I know that the electric field can only depend on how far away you are from the point charge radially, this distance little r. So that motivates use a surface that is a sphere of radius r, or I guess a sphere centered on Q with radius r. And let's move this over. So then I'm going to just imagine my ethereal kind of ghostly surface. Again, there doesn't have to actually be anything there. I can imagine kind of my kind of ethereal sphere that is centered on Q. Actually centered that well. It's centered on Q, and it has some radius r. So I'll just draw this radius here, r. Now, the electric field is always pointing directly away from the charge. But also, if you think of all these little patches that make up the sphere, let me draw that right. So like this patch here, kind of at the top of the sphere. Now the electric field. There's blue for the electric field. Right? The electric field is kind of going out, and it's piercing that surface. There's the electric field. And it's kind of pointing radially away. But then for this little patch also, dA is pointing radially away. So there's, again, where the symmetry is helpful. The electric field, no matter which of these little tiny patches you pick, the electric field is always pointing directly away from the charge, and that also happens to be exactly the direction that each of those little patches, little area vectors are pointing. All those little area vectors are pointing directly away from the charge. So for this surface, we can note two things. The electric field is constant. I guess is the same constant magnitude through each of the patches. Right, the electric field is has the same magnitude through each patch of the sphere. And the angle between the electric field and the patch, in each patch, is 0. And so I guess I'll say E and dA, right, the vector points perpendicular to the patch, are parallel for each patch. So then the dot product is just the magnitude of the electric field times the magnitude of dA, because cosine of 0 is 1. So then, Gauss's law time, the electric field, the flux through this surface, and I'll just explicitly through this red sphere. In this case, because of the symmetry, is the same thing as the integral over the magnitude of E times the magnitude of dA times the cosine of the angle between them, which we said is 1. This E maybe I'll be very explicitly right. We said that this E is a function of R only. So, right, E is a function of R. But then these patches, each patch is the same distance away from the charge. It's the same radial distance away from the charge. So in this case, right, function of R, but R in this case is R in the case of this integral is a constant. But R is constant in the integral. Because what are you integrating over? You're integrating over the patches, and each patch is the same radial distance away. So E is a constant in this case. So this is the same thing as the integral of, I take E out, and then it's just an integral over dA. So then I've just turned this problem into add up all the areas of all these little patches. Well, I don't actually have to do the calculus integral there, because I know from high school geometry what the area of a sphere is. So then this would be it's E times 4 pi r squared, area of a sphere. And dimensionally, does that make sense? Right, it should be r squared, right, because it's two-dimensional. A sphere, a surface of a sphere is two-dimensional. And then by Gauss's law, this better than equal Q divided by epsilon naught. And then look at that. This says that the magnitude of the electric field at a distance r away is Q divided by 4 pi epsilon naught times r squared. There's the magnitude of the electric field, and we had already motivated that the direction should be pointing radial away. We have, in essence, derived Coulomb's law. Not experimentally verified, but derived by using Gauss's law. And again, it amounted to evaluating flux at a surface and relating that to the charge inside. Here, though, we then were clever and continue to use symmetry to help us. Let's do a sheet. I said I have the infinite sheet. So in this case, I have, let me just draw a finite part of the sheet. Right, and this goes off in all directions, of course, forever. And we had derived the electric field before, and I said that this is a very messy multidimensional integral. Your Calc 3 professor will do it for you. Just trust me, it's the charge density divided by 2 epsilon naught. Let's again derive that without needing any any sort of fancy integral. So, so the infinite sheet, and the only thing I think I need to say to specify the problem is that there's with kind of charge density, charge density, lowercase sigma. Which again, remember lowercase sigma, I'll say sigma naught to specify as a constant. Remember, if I just go off to the side, right, kind of the definition of a 2D density, sigma, is that that's telling you kind of the amount of charge dq and how it's spread out over some area dA. If the charge density is 3 coulombs per meter squared, that means that for every meter by 1 meter square I draw, there would be exactly 3 coulombs of charge, right? If it's 3 coulombs per meter squared, every meter squared patch has 3 coulombs of charge in it. So, what do we know by symmetry? Right, we have this sheet that goes off in all directions forever, and we had to ask ourselves what the electric field looks like. And we ultimately said that the electric field has to point kind of, directly away from the sheet, right? Not at an, right? So it had to point kind of, perpendicular to the sheet everywhere, and it turned out to be constant. which we will derive. Right? It can't be at an angle, right? The electric field can't kind of point at an angle relative to the sheet. It had to point directly away. And again, we can make a symmetry argument for that. Right? If I have an infinitely long sheet, right? This is not infinitely long, so that might not work. If I have an infinitely long sheet, I get to say, look at the sheet, and hold it in your mind's eye. Now close your eyes, and then open them again. You would see the exact same sheet. I could have, though, rotated the entire thing. I could have taken the entire thing and rotated it a little bit, but you still would have seen the exact same thing if you had an infinitely long sheet. So again, the electric field can't be at an angle, because then if you rotated it, you would see that difference. So the only way you can have that rotational symmetry is symmetry says that the E field must point kind of perpendicular to the surface. Right, so if I were to draw the E field, it must look something like that. And so therefore, if it's going to depend on any variable, the only variable really that it's allowed to depend on is how far away it is, kind of in this perpendicular distance away from the sheet. Because again, if it depended on kind of little x, little y, and little z, that might not look the same if I were to rotate the sheet. In this case, it'll turn out to be a constant. So the fact that it points vertically upward and downward, right, I could draw some electric field lines below the sheet as well. And again, assuming positive charge density in this case. Just flip all the arrows if you want negative. Here's the sheet again. This thin sheet. It's a two-dimensional sheet in a sense. Or imagine tiny, tiny thickness. The surface I should use, again, I want to pick a surface such that the electric field is either going to be uniform through a side of that surface, or it's going to be, the flux is going to be zero, because either E is zero or E is perpendicular to the surface. So let's use what I feel like sometimes is called the Gaussian pillbox. But essentially I'm going to use just a cylinder as my surface. Right, so eventually the cylinder kind of pierces the surface and then eventually comes down on the other side, and then there it is. So that's kind of a cylinder that kind of goes into the surface. Here, let me actually draw a little bigger. There's the top, and there's kind of where it intersects the sheet. And let's let it be symmetric too. So if this is some distance L, then this is also some distance L. So the surface is a cylinder of radius r. We do have to state what the surface is. So this radius here, let's call it radius r. No, we've been using capital R for kind of the length away from the surface. So let's call this radius A. Radius A and length L. And I've put it, or length 2L, I guess, in this case. With kind of half of it above and half of it below the sheet. Now, again, what does the surface look like when I also include some electric field vectors? So here, if I have to do kind of a blow up of the surface, I should have used red. Here's the top, and then here's the bottom. that a little bit more dashed. And then here's where it kind of pierces the sheet. So then again, this is L, this is L, this is A. Now the electric field, we said only can point, from this kind of patch here, that has some charge. There are electric field vectors that are going up and piercing through the top, and then there are electric field lines that are going down and piercing through the bottom. And again, the symmetry here is great, because if I look at what is the normal vector, the dA, for this top patch, that vector also points directly up. Here, this vector also points directly down, parallel to the electric field. So again, the dot product is simple. But then what's going on with that third surface, the rounded surface, which then I can't draw one vector for that, the side of the cylinder. I have to break into a bunch of rectangles, and each of those rectangles are oriented in a slightly different way. Or maybe it doesn't matter, because you do also know that each patch on the side has a dA that is perpendicular. Right, one patch. Right, this is the electric field. Kind of one patch has a dA that goes this way. Over here, the patch has a dA that goes this way. Maybe over here, a patch has a dA that goes this way. Here it goes this way. So no matter kind of where you are on the side, all those vectors that correspond to the little patch orientations are not. None of them are going up, and none of them are going down. They're all either going out left or right, or into the page or out of the page. So then that means that E dot dA is 0 for all of them, for all those patches on the side. Fantastic. That integral then becomes really simple. Now what is the charge enclosed? The charge enclosed, here is useful that it's a constant charge density, right? Which means the charge density is the same no matter if I'm looking at a little patch of the sheet versus a giant patch of the sheet, right? The density, how the charge is spread out, is uniform. So then we can use essentially dimensional analysis, right? If the charge density is charge over area, then the charge is the density times the area. So in this case, then the total charge enclosed is then going to just be the charge density multiplied by the area. Essentially that area I've shaded in blue. So sigma naught times pi a squared, the area of that blue disk. Okay? You might wonder, well, this A was kind of arbitrary, right? Because we just kind of randomly imagined a cylinder that had a length L and a radius A, but are those variables going to play a role in any way? Well, let's see. Now by Gauss's law, I'm trying to go to the next page. So by Gauss's law, the total flux through the cylinder, our surface that we picked, is equal to the flux through the top, the flux through the bottom, and the flux through the side. The flux through the side, we just argued, was 0, because the electric field is perpendicular to all those area vectors. So that's nice. The top looks like it's just the electric field that's going through the top times the right? And we argued that the electric field must be a constant on that surface, because it can only, if anything, depend on how far away you are from the sheet. And the top of the cylinder, every part of the top of the cylinder is the same distance away from the sheet. So there's the top. And all right, and again, dot product, cosine of 0 is 1. For the bottom, it ends up being the same integral, because again, E is now pointing down, but then the area vector is also pointing down, so the so the angle between them is still 0. The dot product is still the same. And since it's the same distance away from the sheet, right, we know that these two E's I've written down are the same number. Plus the side, which we said was 0. So then it looks like it's 2 the electric field, because that can come out of the integrals. Then it's an integral over just the area of the top and the area of the bottom. So then that looks like it's 2e times pi a squared. And then that equals 1 over epsilon naught times the charge enclosed, sigma pi a squared. I've run out of room. We're going to make this work. I don't want to have the one more line of math on a separate page. So then, what do we conclude? That the electric field must then be equal to, and then look at that, the A's cancel, just sigma naught over 2 epsilon naught. The magnitude is a constant, and by the symmetry, we already said that the direction is it points away from the sheet. And we didn't have to do any sort of Calc 3 integral to do this. We just identified a surface that either made me be adding up a bunch of zeros, or I had to add up a constant over some area, and this is geometry. So I think I won't actually do this example. I'll save it so I can let you guys try it in class, but let me set it up. I suppose you have an infinite wire with charge density lambda naught, again to say it's a constant, where again, just to remind us, lambda naught is the amount of charge over the length of the wire, so we might say dx. Right? If we orient it along the x direction, if it's 3 coulombs per meter, every meter of that wire has a total charge of 3 coulombs. And then we were able to show that the electric field points perpendicular away from the wire, and the magnitude is a function of r. In this case, not sigma, but lambda, sorry. Blanking on my Greek letters. Right, and then we wrote this as kind of lambda over 2 pi epsilon naught times capital R, where at some point away from the wire, I could define a distance r, where I used the different distance that was kind of perpendicular to the wire. And then the electric field there was lambda over 2 pi epsilon naught divided by r, capital R, not r squared or little r. So how might you go around proving that with Gauss's law? I will set it up, and then I will let us do that as a problem in class. My suggestion is to, for this one I'll give the hint of, consider again a cylinder that has, maybe we'll say some length L, and again we'll stick with some radius A. Let that be a finite cylinder such that it does encapsulate a finite amount of the wire. So again, there is a finite amount of charge in that cylinder. Think about, so then I would think for this problem, by symmetry, kind of what can you say about the electric field? Then write the flux through, then look at what is going to be the flux through each of the sides of the cylinder. And I claim you can think of it only in terms of the left cap, the right cap, and then the rounded part. And then also, what is the enclosed charge inside that cylinder? And then Gauss's law all the way. God, I'm already at an hour and 10 minutes. All right. Well, I guess there was one more example I wanted to do, but I think it's also going to be a problem we work on in class. But again, let me sketch out the idea here. Is using Gauss's law, we can actually end up saying something very powerful about, say, what the electric field looks like inside a conductor. So suppose this is a conductor. But again, remember that just means charges are allowed to move around freely if they want to. And again, the electrons are moving around. A conductor, but then what if you have a conductor with some net charge? Right, some electrons are added or taken away. Some conductor with some net charge, capital Q. We could ask questions like, where is the charge? Where is that net charge? Right, we know everywhere in the conductor, right, there's atoms. If this is a big block of copper, right, there's protons and electrons everywhere inside. But if I add on some additional electrons, then those electrons, right, that are free to move around will want to distribute themselves some way on the conductor. Where does all that excess charge go? Since that's what matters. Right, since it's the excess or the net charge that impact the eventual electric field. Where does that charge go? And then what can you then say as a result about the electric field inside the conductor, at the surface of the conductor, and maybe just like a sliver right above the surface of the conductor. Now what if I were to carve a hole inside the middle of this copper kind of chunk? Does that change anything? So we will motivate that through kind of a scaffolded set of problems, I think, for the work we'll do in class. All right.